Hello everyone, I'm Depanshu Sani and I will be giving a brief overview of our work on Hier-COS, making deep features hierarchy aware via composition of orthogonal subspaces. Similar to any machine learning algorithm, classification algorithms are also prone to errors. But in many real world applications, we have observed that all mistakes that we make are not equally wrong. Therefore, we can say that for any class label, like car, there exists a partial rank order over the negative classes that defines the severity of mistakes. Our objective is to design a classification algorithm such that we learn to make less severe mistakes. In the literature, this has been achieved by learning a hierarchical image classification algorithm, where the objective is to learn feature representations for all the classes such that the distance between the classes in the feature space is directly proportional to the distance between them in a known hierarchy tree that encodes the severity of mistakes. In a general classification framework, the objective is to learn feature representations such that the feature vectors align with the direction of the weight vectors. Instead, we propose that the feature vectors can live in the span of these weight vectors like this. We propose that the weight vectors are fixed to be orthogonal. Therefore, we can say that the weight vectors for truck and car form the basis vectors for the 2D plane, which will always contain a vehicle. Using the hierarchy tree, we now have the notion of composing the basis vectors to get the coarse level subspace. However, this framework still does not ensure that the feature representations respect the hierarchy tree, since all the classes are still orthogonal to each other. For this, we define the feature space to be higher dimensional. Specifically, the dimension of the feature space is defined to be equal to the number of nodes in the tree. Now, whenever we want to represent a car or a truck, we know that these classes also belong to a vehicle and therefore should also span the vehicle dimension. Following the same hierarchical composition formulation, we can say that any vehicle will always be constrained to live in the vector space that is defined by the basis vectors for vehicle and all of its descendants. Due to this hierarchical composition of vector subspaces, we observe that whenever there are no common ancestors between two classes, the vector subspaces for such classes are always orthogonal, like we see for vehicle and vulnerable road objects. On the other hand, the angular separation between classes within any subspace is less than orthogonal because of the common basis vectors that we have in the subspaces, for example, the common vehicle dimension. This formulation allows us to define a subspace for all the nodes in the tree by the generic definition that the subspace is spanned by the basis vectors for itself, all of its ancestors, and all of its descendants. This formulation allows us to learn a unified model to do hierarchy-aware fine-grained as well as hierarchical multi-level classification. Additionally, it theoretically guarantees that the multi-level predictions will always be hierarchically consistent. We compare our results on multiple datasets varying in height, number of classes, and total number of nodes in the tree. The comparative results across all the datasets with the existing state of the art are summarized here. We observe that our method does not have improvements in terms of hierarchical performance that quantifies the severity of mistakes. Upon analysis, we observe that all the existing metrics are limited as they do not capture the true hierarchical performance. Since accuracy considers all mistakes to be equally wrong, it does not capture the hierarchical performance at all. Mistake severity metric computes the LCA distance between the correct and the incorrect classes. Since the LCA distance is only computed and averaged over misclassified samples, it is biased towards making more but less severe mistakes. Due to this, mistake severity metric is always coupled with the accuracy metric, thereby resulting in a multi-metric evaluation. Average hierarchical distance at K tackles this by computing distance over all the classes. However, it takes an average over the top K predictions. Since average is a permutation invariant operation, it has the exact same performance for any permutation of the top K predictions, which is not desirable. This is a handcrafted example which demonstrates the limitations that we just discussed. To analyze this more closely, we plot the percentage of samples that were predicted with the correct prediction order for the top K classes across all the datasets. We observe that the performance of our model is indeed better than all the previous methods across all the datasets. In fact, we observe that for the real world dataset, which is tiered ImageNet, that has the where the hierarchy tree is the most deep and complex, the performance of the existing state of the art drops from more than 70% to less than 50% in just top 3 predictions, while we almost maintain the same performance across all the top K values. Based on this, we propose a new metric called hops, which intuitively quantifies the weighted percentage of all classes that are ordered according to their hierarchical preference order. And based on this, we observe that our method outperformed all the existing methods across all the datasets. And since our method is the first one to learn a unified model to do hierarchical multi-level prediction, we also compare its level-wise hierarchical performance with the other methods that train intermediate course level classifiers, and we outperform all of them. Finally, we also show that our method is also hierarchically consistent. Thank you.